Hi, my name is Kat, and I would like to share with you one of my favorite images, Earthrise. So this was taken by Apollo 8 in the 60s, and in the decades since then, we've been able to explore the solar system further and beyond. In fact, we've been able to image planets around other stars. This is HR 8799, one of the self-luminous giant planets that current direct imaging surveys are able to study in the near infrared. And then on the flip side, in terms of smaller planets, we've been able to study those around ultra-cool and low-mass host stars using transit spectroscopy. And then looking decades after today, we have the James Webb Space Telescope coming online, and we have WFIRST, HabEx, and LUVOIR. And what do these three have in common? They're all interested in imaging exoplanets around sun-like stars in the visible. Take WFIRST, for example. Here we have the planet-to-star contrast ratio versus separation, and this is what I was mentioning earlier about the self-luminous giant planets for the current state of direct imaging. With WFIRST and its coronagraph, we're going to be able to cover this part of the regime to study non-transiting planets, and those that are cooler in temperature. And then coming down over here, if you recall to Maggie Turnbull's talk on Monday, where she mentioned the possibility of pairing a starshade with WFIRST, this, once we overplot the contrast curve for WFIRST with a starshade, this is where we have the solar system planets at 10 parsecs. So this tells us that WFIRST might have the possibility of imaging rocky exoplanets in the future. And so when these missions take the images of the planets, we're going to get spectroscopy on them, and we're also going to get data that are noisy, and the challenge will be to backing out the properties of these planets. And given the data quality, we want to know how robustly will we be able to get those information. And more importantly, how do we quantify that? So I'm going to be talking about how we use how we're going to simulate data in order to, we're going to simulate data, and then we're going to build a retrieval tool that will then help us constrain those properties based on our simulated data. Okay. So let's start with the spectrum of the Earth. Here we have the brightness versus wavelength going from the near ultraviolet to the infrared. And all three missions that I mentioned are going to be interested in exploring the possibility of imaging the visible wavelength. And in this particular region, there are many interesting features that we will capture with our model. To begin, we have the nitrogen Rayleigh scattering, and then we have water absorption, that I will mark somehow. Yes, Rayleigh scattering, water absorption, ozone absorption is over here, and then there are oxygen features as well. Oh, all right, thanks for the tip. Awesome, great. So those are the features that we're going to recreate in our model, which is basically a planet, its visible hemisphere will be divided into 100 points, and for each point, we're going to run radiative transfer on it, as well as including scattering to determine the geometric albedo overall. And then we're going to translate that into the planet-to-star flux ratios, which is what we're going to be able to observe. And speaking of what we're actually going to be observing, it's going to be something that's lower in resolution. So here I have an example of planet-to-star flux ratio versus wavelength at a resolution of 70. And what's more is that these data are going to be noisy. So in this case, we have a data set that are signal-to-noise ratio, or SNR, of 20. And what's going to be really informative is if we have a way to justify a certain signal-to-noise ratio that will allow us to quantify constraints on water vapor or oxygen. So in this case, I have a spectrum that's signal-to-noise ratio of 10. And so how will that do in comparison to the signal-to-noise of 20? And would we be able to get away with a signal-to-noise of 5 and still get the amount of constraint that we would want on interested quantities? So we aim to understand what information is present as a function of signal-to-noise ratio. And to do that, we're going to use a Bayesian retrieval framework that Chu Hong introduced the concept pretty well earlier this morning. And essentially, we're going to have a bunch of input parameters that have prior distributions that we'll draw from and construct one set of parameters. We're going to put it into the forward model, which generates a high-resolution albedo spectrum that we then bin down to the resolution of the data, and this is when we'll get to do the interesting goodness of fit comparison by feeding it into a chi-squared likelihood function. And then it's going to be an iterative process where we'll draw from those prior distributions again and again and compare that goodness of fit again and again until we construct the posterior probability distributions for each of those parameters. Another way of thinking about a retrieval is this is a very data-driven method. So for a given set of data, and we propose a set of parameters, there's going to be a corresponding spectrum that follows that proposed set of parameters. And then for a given range of parameters, there's going to be a range of spectra. And so we'll be able to visualize the spread in our confidence in terms of how well our model fit the data. So here we have red is 1 sigma for the spread. We have coral, that's for the 2 sigma spread, and then there's also a blue line over here. And I just want to say that we're using I think I forgot to mention, we're using the noise model that Ty Robinson created for coronagraphs. And in terms of the larger error bars over here in the red end, this is partially due to the fact that there are fewer photons from the host star in this particular part of the spectrum, and the detector quantum efficiency in the red end tends to fall off, or at least that's the case for a W first type scenario we're considering. So going back to this idea of posteriors, I'm going to start with an example where we only have 2 free parameters. So this is an atmosphere with a surface pressure that we're going to retrieve for and water vapor, and we're assuming we know everything else. So here are those posterior distributions after we perform the retrieval. And you can see this is for water, this is for surface pressure, and then the blue lines indicate the true input values. And the power of the retrieval method is that we're able to attach uncertainties to our estimates. But of course, life is not that easy. We are not always going to only have 2 unknowns. So we've developed a forward model where we have 9 retrievable parameters, and this is a set of parameters that we think represents the minimum number of parameters that are necessary in order to recreate an Earth-like spectrum. So we have surface pressure, surface albedo, the mixing ratios for water, ozone, and oxygen, and we have a cloud layer that has a cloud top pressure, delta P, an optical depth, and then an F cloud parameter to represent fractional cloudiness. And for the sake of not being too complicated, we decided that we want to assume that we know the radius, the semi-major axis, what the background gas is, and we're also implementing an isothermal pressure-temperature profile. So once our forward model is assembled, we're able to simulate the spectra between 0.4 and 1 micron at a resolution of 70 and for 4 different signal-to-noise ratios. So first up, we have the results from the signal-to-noise ratio of 5 data. And just by eye, you can tell that there's not going to be much information that the data will be able to give us. And we see that very well with the spectral fits. And I've marked the water features over here because I'm about to walk through the posterior distribution for water for each signal-to-noise ratio so you can see how that changes once the data get better. So first, it's the same signal to noise, and you can see, so this is log of water vapor mixing ratio, and this is the true value. So there's no detection for this SNR. Going up to SNR of 10, there is still no detection. And we step it up to SNR 15, and this is where it got really awesome, where we were able to get a constraint on the water vapor mixing ratio. And returning to that comparison to the spectra, you can see in this case, we actually are able to trace out the features much better, and that's because we have that constrained water vapor now. However, water is not the only thing we care about. And if we look instead at the broader picture, and we think about the gases we're interested in, water, ozone, and oxygen, we see that in this case, so this is water, this is ozone, this is oxygen, comparing SNR 15 and SNR 20, you can see that it is only with SNR 20 that we are able to actually constrain all three molecules. So this shows us that retrievals are actually able to allow us to make these statements, and not only that, we're able to back it up with quantitative reasoning. So moving forward, what we're excited about implementing is connecting or expanding beyond just studying Earth-like planets. We want to be able to model super-Earths. We want to be able to model mini-Neptunes, because those are, as the Kepler mission found, are the most common small planets in the galaxy. And then, as Sean alluded to earlier, we're going to expand our wavelength range such that we can accommodate the interests of HabEx and LUVOIR as we move forward in exploring what types of data will be able to enable our accurate inference about an atmosphere. And then furthermore, we want to be able to implement wavelength-dependent surface albedo. So Jake, who's speaking after me, will be able to tell us about how important it is to consider the heterogeneity for the surface of a planet. So to wrap up, we have created a retrieval framework that is able to allow us to quantitatively say how confident we are in our understanding of a terrestrial atmosphere when observed with a future space-based coronagraph or a starshade imaging mission. We have studied simulated spectra from 0.4 to 1 micron at a resolution of 70, and we found that it is only at a signal-to-noise ratio of 20 that we're able to constrain quantities like water, ozone, and oxygen altogether. And moving forward, there are lots of things we want to be able to implement, and so I would like to hear what your thoughts are and take any questions. Thank you.
That was a great talk. In terms of the inputs for your model, let's say one of these flagships gets selected, is flying into the 2030s. How important are the prior knowledge of the semi-major axis, the radius, or we might be able to get a limit on the radius from a dynamical mass? How important is the information on the planet before the mission actually flies and we get a few images? And how critical is it, or do you think you can, there's not enough degeneracies, you might be able to get away without that information?
So in terms of radius, we have already tried retrieving on radius, and in fact, if you refer to Michael Nyack's 2016 paper, where they're looking at Jovian planets in the reflected light, they retrieve for radius. And so that is something that we might be able to put constraints on ourselves, because it's going to be difficult to actually measure that for a planet. But for semi-major axis, I think that'll be really important to know well in terms of getting the uncertainties on that down, because that could impact just where the data sit. And so, but we haven't looked into throwing that into our retrievals. So at least for the semi-major axis, I would say that would be something in terms of astrometry we would want to be able to get well.
Hi, Kat. Avi Mandel from Goddard. One comment and one question. The comment is, you probably are aware of this, but I'd like to hear what if you guys have started exploring it. Each of those points or parts of the spectrum will be taken on with different observations with W first, at least. You'll get an optical band, you'll get a certain IFS band, and so it'd be really nice to be able to prioritize one observation or a set of observations rather than saying we need the whole spectrum. Mm-hmm. Have you guys started doing that, or is that?
Yeah, so we have an instrument model set up right now where we have the two blue filters, as well as the from 690 to
600
to 900 nanometers
900.
Space. So we have that set up. We have yet to separate those three IFS bands, though. And I know that some parts of the spectra, they overlap, so it would be interesting to think about that in terms of having very good signal-to-noise ratios in that particular area. So we're like halfway there.
Okay. Yeah. And my question was...
Sorry, we're going to have to cut the... Oh, you're...
I just had one short question.
Yeah, really short.
Can I say, it was just you said you took all the points on a hemisphere, and yet you have a globally averaged profile. Why do you have to use all of the individual points across your hemisphere?
Maybe it was my wording that was
Okay.
off about the globally average. Yeah, we can talk later. Thanks.
All right, let's give Kat another round of applause.